Hey everybody, it's Ridley. I'm back again. We're in section 2.4. We're talking about continuity of a function. All right, now let's go back to our limits. If I have a function, whoop, right here, and off it goes, right? This, if I call this x equals a, and this guy's name is f of x, I know that the limit, let's call that L, the limit as x approaches a of f of x equals L, because if I sneak up on that point, x equals a, my fingers are going to touch, even though I do not care about x equals a. However, if I want this function to be continuous at this point, continuous at a point, so we're talking here about continuity at a point. All right, let's define point continuity first before we start getting into the more nuanced aspects of continuity. What does that mean? Well, think about it in terms of my little stick your fingers on the graph analogy here. Not only do my fingers have to approach the same value, but what must they do if it's going to be continuous? Just based on our intuitive understanding of continuous functions. It means we can draw them without lifting our pencil, right? Problem is, if I try and draw this function without lifting my pencil, I got to go whoop. And this point right here at x equals a, it gives me a discontinuity, right? So if we're going to have continuity at a point, what does that imply? Well, it implies that the limit as x approaches a of f of x must be what? It has to be f of a. In other words, so remember back in the day, you probably played with the, whoops, let's do this guy right here. If I had a point down here, the limit still existed, and the limit was still L. But clearly, I'm not continuous at x equals a. So what we have to do is we have to shove this point in here to make sure that when I sketch my graph, whoops, I pass, whoop, right through. I don't know why I'm going whoop, whoop. Don't ask. All right? So that's the definition of continuity at a point. Now, once we have continuity at a point, we can talk about continuity of an interval, or on an interval. All right? So think about this. It's really simple. I can simply say this is just going to be a definition, right? And I'm going to say f of x is continuous. Now, I'm not going to write continuous anymore. I'm gonna abbreviate it with CTS. Why? Because I'm a mathematician, which means I'm lazy. Is continuous on an interval from A to B. This can be opened or closed. We'll talk about the endpoints here in just a sec. All right? Is continuous on the interval from A to B if it is continuous at all points. Now I'm going to get fancy here with a little math speak. X in AB. In other words, you grab any element of the interval from A to B, and f of x has to be continuous at that point. So basically, you take the sum total of all of the points on the interval, and the function's going to be continuous at all of those points, which implies that it's continuous on that interval. Okay? All right, now let's talk about some discontinuities. What we kind of have an understanding, hopefully we're starting to wrap our brains around what continuity means. Now let's talk about discontinuities for just a sec, because there's a few types, and you're going to have to know what those look like. Discontinuities. All right? All right, so the first is called a point, or a jump, or not a jump, excuse me. A point, I guess you could refer to it as a jump, but this is also referred to as a removable. And I'll show you why in just a sec. Discontinuity. All right, and what does that look like? Well, it looks like this original graph over here. All right, so what I've got is I have a function, and I end up with a point. All right, now I'll talk about how to remove it. Now let's think about this. We've already dealt with these guys before. If I take the limit as x goes to 2 of x squared minus 4 over x minus 2. Well, we know from past experience and from algebra that because if I plug it in, I get 0 over 0. Es muy malo. So I'm going to do a little bit of algebra, and I know that this equals the limit. If I factor x squared minus 4 divided by x minus 2, I end up with x plus 2. And this ends up being 4. So what I end up with is, I end up with this function right here, but at 2, I've got a hole. Okay? Now, how could we remove that discontinuity? That's clearly a point discontinuity, right? How could I pull that thing out so that I no longer have that discontinuity? Because in calculus, sometimes we're going to need to be able to talk about continuous functions. Having continuous functions is one of the cornerstones of being able to do a lot of things in calculus. Well, let me show you. Change the color on my pen. All right, it's real simple. I cheat. I'm going to let f of x equal, I'm just going to do a piecewise function. I'm going to let it equal x squared minus 4 over x minus 2 for x not equal to 2. Because we know that this function is not defined at x equals 2. No matter what we do, it's not defined at x equals 2, right? Now, this guy is defined at x equals 2, but these two aren't the same. This function has a hole right here. This function has no holes. And then all I do is fill the hole. I just stick in the value of the limit when x equals 2. And what does that do? Whoop! It just fills the hole in. Guess what? I got myself a continuous function. All right? So that's an example of a discontinuity that can be removed. All right? Number 2, there are infinite discontinuities. All right? What do those look like? Well, think 1 over x. That's kind of the easiest one to think about. Yo. All right? Now, what do I have? I have an infinite discontinuity at x equals 0. Wow, I don't know what just happened there. At x equals 0 because all hell breaks loose, right? My functions go in all sorts of different directions. Now, let's be really careful here for just a second. Let's talk about y equals the natural log of x. We know what that looks like. It looks like this, passes through the point 1 comma 0. The question that you have to ask yourself, okay, does this function, y equals ln of x, does it have a discontinuity at x equals 0? Well, the function isn't defined at x equals 0. So of course it has a discontinuity. There's no limit. I can't talk about a limit. If I can't talk about a limit, then I can't talk about continuity. Okay? It's also not defined for any values to the left of x equals 0. However, the natural log of x is continuous for all values of its domain. There are no points on its domain where all hell breaks loose, right? I can draw the entire function. I can draw the entire function without having to raise my pen. I just can't draw it for all reals. So this guy right here is continuous in its domain, but it's not continuous in the reals. All right? Now this guy right here is, now think about this. This will make you kind of crazy. It is also continuous in its domain, right? It's not continuous because remember what its domain is. The domain of this guy is negative infinity to 0, union 0 to infinity, right? So in its domain, you pick any point between negative infinity and infinity, as long as we're not talking about x equals 0, this guy's going to be continuous. But it's not continuous in the reals. However, we know the exact value, x equals 0, for which we get this infinite discontinuity. All right, now let me give you an example of functions which aren't continuous even in their domains. All right, these are called jump discontinuities. I'm not going to change colors, I'm lazy. Jump discontinuities. And this happens, do you guys remember the greatest integer or the least integer function? That was the one that we used for like cab fares and rates like that. So if I have this, and I've got a function that does, whoops, and I've got a function that does this. So let's say, whoops, I've got a function that goes here, and then goes here, and then goes here. What am I getting? I'm getting jump discontinuities. I'm having to lift my pen to draw it. Now, look at this function. It would appear, let's assume that this goes on forever in both directions, right? So I'm going to have these guys like this. The domain of this function is all reals. So this thing is neither continuous, it's not continuous in either its domain or in the reals. All right, it just so happens that its domain is the reals. But let's say that we were just talking about the right-hand side. Then it would be discontinuous in its own domain, because now with this guy, my domain appears to be from 0 to infinity, right? And this would be discontinuous because it's defined for all values between 0 and infinity, and it's got these jumps. All right, so those are examples of discontinuities, and you got to keep your eye out for those because the calculus really breaks down at points of discontinuities. Now, let's talk about a function like y equals the square root of x. All right, wow, that's a badly drawn coordinate plane. Let's talk about this guy. So what do we know here at x equals 0? Well, we know that y of 0 is equal to 0. We know that it's defined. We also know that if the limit, let me do this, I got to break this apart a little bit. We also know that the limit as x approaches 0 of the square root of x does not exist because I can't approach it from both sides. However, if I took the limit as x approaches 0 from the positive side of the square root of x, that should be up a little bit, sorry about that, I know that that equals 0. So let's talk about, for just a sec, let's talk about continuity at endpoints. Okay? Because that's going to give us the ability to at least kind of play with functions like y equals the square root of x. Well, it's real simple. Check it out. I know that the limit, if, and this is going to be another definition, so we'll put a definition up here. If the limit as x approaches a from the positive side of f of x equals f of a. Now, what does that mean? That means that for some function at an endpoint, let's say the square root of x, as I sneak up on this thing from the right-hand side, like that, I know that if the limit as x approaches a from the positive side equals f of a. In other words, it's headed for the same value. It's headed for the value of the function. In other words, the limit and the value of the function are the same. We say that this is continuous from the right. From the right. And without loss of generality, if the limit as x approaches a from the negative side of f of x equals f of a, we say this is continuous from the left. And what that really does, I mean, if you're just dealing with a regular old function, you could talk about continuity from the left and from the right. But what it really gives us the ability to do is talk about functions that end. Like, let me give you another example. F of x equals the square root of 9 minus x squared. All right, well, what do we know that that is? Hopefully, at this point, you're kind of getting to a place where you see that this is the top half of the circle of radius 3. So this is -3, and this is 3. So it's still a function, it's still useful, and I can play ball with it. I can do calculus with it. But I want to make sure, like if I take the limit as x approaches, let's go -3 from the negative side. So I'm going to sneak up in this direction because it doesn't make sense to talk about values to the left of -3 because f is not defined for those values of f of x. Well, if I plug it in, guess what I get? I get 0. All right, which implies this guy is continuous from the right. Similarly, I've got different colors. I should utilize them. If I take the limit as x approaches +3 from, wait, my bad. Sorry, guys. This should be a positive. Yeah, you got to yell at me when I do stuff like that. I'm approaching from the right, which means, oops, I'll try and throw a pop-up in there that says ding dong. All right, if I'm approaching +3 from the negative side of f of x, well, when I plug it in, I get 0 again. Look, sneaking up from the left-hand side, which means that this is continuous from the left. Okay? All right, so again, I was consistent up here, and I was inconsistent down here. Sorry about that.